So, ladies and gentlemen, it's time to start our final session. So please take your seats. Our first speaker of the current session is Nagy Dániel, who will speak about heterogeneous CPU-GPU ordinary differential equation solvers. So please start.
Thank you very much. So I'm Daniel Nagy from the BMN Department of Hydrodynamic Systems. I'm a PhD student there. About the motivation shortly. So at the department, we are using GPUs to solve ordinary differential equations for more than 5 years. But recently we have encountered some problems where the pure GPU approach, maybe it's not the best, and some heterogeneous CPU-GPU computations should be used for optimal performance. In this talk, I want to elaborate on actually only on some little experiments we have done so far in this topic, because so far this work is not final, so it's some experiments we have done so far. So the goal is to develop a heterogeneous CPU-GPU or the differential equation solver. In this work, we are using CUDA. And yeah, we would like to use both the CPUs and GPUs to have the most optimal performance and speed up the solution of parameter studies. What are those parameter studies? In those parameter studies, we usually systematically examine the behavior of a dynamical system. Let's say we have a differential equation which describes, for example, a pendulum or an oscillator or something like that. And of course, based on the parameters, we might have different stable states and interesting phenomena like periodic orbits. So usually we do parameter studies to explore the bifurcations of a dynamic system or something like that. And where we encounter problems was at the delay differential equations, because if we solve delay differential equations, we must also know the path. So it's not enough for the GPU to know the current state of the system. We must also save a lot of past data about the system to calculate the delay terms in those equations. And for those problems, we had problems applying on the only GPU approach because the memory load was just too much. And the GPUs were actually so slow that a simple CPU code performed better. So that's where the idea came to, let's try and develop a heterogeneous solver. First, how do we solve differential equations on GPUs and why? So we have an ordinary differential equation here. So the derivative is equal to a function of the state x and the time. And of course, we have parameter or vector of parameters. Of course, why we do this? Because we usually, for example, in our work at our department, usually some parameter is uncertain, or you can modify the parameter quite easily, and based on the parameter, the system behaves differently. So sometimes in a large parameter space, it can happen that you have millions of different possible parameters which should be checked. And how to solve it numerically on a GPU? Well, let's say we are using a traditional forced order Runge-Kutta method. This is quite efficient for simple problems. So we calculate the next time step like this. Here, n is the actual time step, and this I is the thread index. So what's happening with the pair thread approach is that, and here you can see that to each thread uses the different parameters. So what we do here is to use the GPU threads, and each GPU thread solves the same equation, but for a different parameter p. And here in this approach, like the threads do not cooperate, they do not exchange data. they just do the same thing for different parameters. It's really good because at the same time, well, we can solve thousands of equations. While on the CPU, you can only do usually one, maybe a little more because of factorization and things like that. But this first approach works really well for simple differential equations. We also published it 2 years ago to compare to other software, or like compared to MATLAB, for example, it is like more than 100 times faster to use this kind of implementation. But even compared to proper only CPU, C++ implementation, it's much faster to use GPUs for this with this algorithm. I mean, of course, there are problems with thread divergence. For example, if we are using an adaptive numerical method, it can happen that a time step is rejected, and then it needs to be recalculated, and it leads to thread divergence. Register fields are also problematic. For example, we use this scalar-Lewis equation quite a lot, which describes bubble dynamics. It's a second-order ortho differential equation with like 20 parameters, and storing all the parameters is too much for the register, so it spills out to cache and sometimes to global memory, especially when higher order numerical methods are used. And this, of course, slows down the calculations. Calculating delay term, for example, in the delay differential equation is problematic because it leads to uncalled memory operations and a lot of memory load. And sometimes, if we would have like coupled systems, which sometimes we also encounter, then we need to store the coupling matrices, and also it cannot fit into the register memory, so we need to do something about that too. Well, in this work, the idea is to overlap the GPU and the CPU calculation, and also the memory operations. For this, I'm going to use CUDA streams. CUDA, it's a sequence of operations that execute asynchronously, and basically with that, we can concurrently execute multiple tasks, and also like hide basically the memory operations. So the host to device and the device to host memory operations can be done simultaneously. And how to translate it to solving differential equations? Well, let's say we have lots of parameters, and each stream is going to handle 1/4 of the parameters in an ideal state. And let's say each stream does the following algorithm. First, we copy the data, the state and the time data from the CPU to the GPU. Then we call the kernel. The kernel calculates one numerical time step and calculates the next time step. Then we copy the data back from the GPU to the CPU. And then the CPU does some operations on this state. In an ideal case, when each substep requires the same amount of time, and then here we have 4 streams, and we can see that after the first few steps, like we will have a perfect overlap. So at the same time, we have a GPU kernel working. The CPU is also doing calculations, and simultaneously we are copying from device to host and host to device. I mean, to test this idea, I have selected 2 very easy test equations. First, we have this Bernoulli type order differential equation. This is quite simple. It can be solved analytically. There's an analytical solution. It is just used for validation. It's pretty good because the solution is this, and pretty easy to check if our code works well. And here we use the standard fourth order limited method to solve it. And the task here is to simulate until t equals to 100 for those parameters, and the parameters are between 0 and 5. The other is a little more interesting. This is the Duffing equation. It's a second order differential equation with a forcing term, and there is a parameter k. And based on the parameter k, we have bifurcations. So here in the system, what we can see, for example, for this 0.22, we have a periodic orbit here. This is a Poincare section. So how this graph is created is that we are simulating, we are running the simulation until more than 1,000 cycles, and then for 32 cycles, at every 2 pi time, we basically say where the system is. And so, for example, here we can see that we have a periodic orbit because the system is either here or here. But of course, if we are going that way, um, for reference, I mean, we can use this MATLAB or 5 goes through these parameters to create, let's say, 10 to solve for. It would take like 2 hours in MATLAB, but on a GPU, it can be done in less than a minute. So let's go to the results. So how this, so first about the Bernoulli type differential equation. So here in this graph, you can see the number of parameters, which is in our case equal to the number of threads and the runtime on an NVIDIA GPU. So here the bread is the pair thread approach, which is when we only use the GPU, and the streams is the streams approach when we are using the NVIDIA, I mean the CUDA streams in the blue one stream and in the green one 3 streams. What we can see here, for a large number of parameters, it scales linearly, and that the pure GPU approach seems to be much faster. And also, there's not much improvement by using more streams. The problem here is that a single Runge-Kutta step requires much less time than the memory operations. So here we have the 3 streams, and here the blue one is the Runge-Kutta step. This is profiling done with NVIDIA Visual Profiler. But all these brown blocks are the memory operations. So the problem became much slower because we are copying data between the CPU and the GPU back and forth. So it's not really optimal. And also the CPU doesn't do much in this case. The CPU was just used to accept the time step or not. So it didn't do much useful work in this case. In the second test, the Duffing equation, it's again, the red pure GPU approach is the fastest. And here what we can see is that it was run with 1, 2, and 4 streams too. And it seems like here, if we use 4 streams, it's of course much faster than 1 stream. But what we see in the end is that also here, CPU calculations are short. But the really important thing, what we could see is that, so this is the blue ones are the GPU kernels. Basically, there are very little gap between the kernels. So that's pretty good because the GPU is occupied and kernels are running. And here we can see the memory operations, and we can see that basically we could do the overlap. So the memory operations and the GPU kernel is overlapped, but of course here the CPU calculations are still missing because the CPU was not doing much. So in conclusion, it is possible to overlap the calculations, but for the given test problems, it was slower than the pure GPU approach. It's mostly because the global memory operations are slow. And it can be good if a lot of serial calculations are also required. And here I go back to the adaptive delay differential equation solver. And I mean, for the next few months, my project to implement this using that way, because for that, at least we think so that this heterogeneous approach would be much better than a pure CPU or a pure GPU approach. So that's all I wanted to say, and thank you very much for your attention.
Is there any question?
Two, actually. The first one is how big is your input data size, what you copy from the host to the device?
So it depends on the number of parameters, because for each parameter, let's here we have, I mean, the state variables, which is to...
In the second case, when you had the stream, in that case, what was the...
So even here, it's not much because it's 100,000 times 4 doubles.
So why do you copy it back and forth? Why don't you just
Because the idea
keep it
is
on the
that,
GPU?
yes, because I mean, it's not implemented yet, but for later, for the delay differential equation solver, we will need to operate on the CPU in some serial way. We have to manipulate the data on the CPU too. It's not implemented here yet. That's why this is not that useful yet.
Okay, the second question is, if you go to the next slide, I'm just wondering whether the kernel time in this case, is it the same as the kernel execution time in the pure per thread version?
No, it's not because it involves some. So one thing is to copy everything to the global memory, but from the it also involves copying from the global memory to the compute core. So it's also involved here. So these kernel times are longer than in the pure GPU.
Yeah.
Because data cannot be reused.
Okay, well, I don't know the details, but I was just thinking maybe the stream actually, you can have a situation when you don't have enough resources to run the kernel basically at full speed, let's say. So every now and again you have to stop the kernel and something else takes over, and that can, so you don't get exact overlap, just partial.
Yeah, it's
resources, and that can be the effect, but maybe it's something else. Okay, sorry, I was not clear enough, but I think you understand what.
yes, I understand. Thank you.
How long is the delay group that you need to consider for your delay differential equation? How many terms or how big period is required there?
It depends really on the problem, but for what we want to use in bubble dynamics, we have to store like 10,000 times. So
yeah, that's a lot.
Yeah.
Thank you.
So is there any other question? Then let's move on our next speaker.